with some specific crosstalk cancellation techniques. And here a little bit about myself, my experience. Start my PhD in UCLA in 2010. And so I start working with some early chiplet interconnect project, and that's to connect 3D and 2.5D CPU and memory interface. And then after that, I got sponsored by the Broadcom Young Scholar Fellowship and working with the Broadcom together. At that time, my advisor is Dr. Afshin at Broadcom, and also Professor Frank Chang at UCLA. And then at that period of time, we developed a 3D chip-to-chip wireless communication technology we called RF Interconnect. And we start up a company called KISA, and it's invited by the Intel Samsung. And I think in 2021, it's required for Molex for the module-to-module wireless interconnect technology. And then after I graduate, got my PhD degree, and I co-founded Kiro. It's an edge AI chip company, and my team lead the first generation of NPU for mass production, and that NPU is for smart home application at the time for face and the recognition and hand gesture tracking or something application like that. It targets on the low power in the IoT smart home application. And then in 2019, I joined the Nanjing University, and at Nanjing University, the main research direction is for chip-to-chip interconnect, and which is related to my PhD project. And also, I'm working on some machine learning hardware accelerators design, including the digital NPU or the mixed signal computing in memory. And also, I have some optical and electrical hybrid accelerators in my research. But today, my topic will focus on the chip-to-chip interconnect. And here's the outline of my talk today. And first, here's this picture shows the algorithm, and the red line is the AI training computing demands. We can change. You can see it change very fast. And the green line is our hardware performance. The hardware AI, especially GPU chips, can provide the computing power. And the bottom line is the interface between the memory, between the computing unit to the memory, or between the different computing cores. And that's we can see there's a large gap between the algorithm application demands and also the computing power demands. And then the slowest, so the bottleneck is the interconnect bandwidth between these modules and chips. And here's some large language models operation we can find this. This is the roofline model. The curve shows most of the computing limited. Is the operation limited? Is at the bandwidth limited? And the roofline is the computing limited. So most of the operation is limited on this bandwidth. And then here's another experiment running on the GPU, seeing also if we just run some burst mode for the inference of the large language model application of GPU, only less than 20% of the computing power is in use. The reason is the data don't have enough data bandwidth. Even GPU already use the best interconnect technology, like the NVLink, NVSwitch, or all the inter-chip and inter-module high-speed links. even in that situation, and also the best packaging technology. Even in that condition, the bandwidth is still limited. So let's see what's the interconnect technology used in GPU. So the first level is a Blackwell die. That's one side of GPU, and then two GPU is. Let's see. Is there a laser?
The best laser in the world.
Thanks. Okay. This one. I like this better. Thank you. You can see this is one GPU die, and NVIDIA connect this two GPU die with the die-to-die interconnect. That's I'll show the spec, detailed spec later. And then this two spec GPU has 200 billion transistor. That's a chiplet technology. And then a GPU die that's connected by the two GPU die and the HBM memory. This is the memory, and it has 8 terabytes per second memory bandwidth in the is the Blackwell GPU. Yeah, I showed here's the interconnect technology the NVIDIA use. And this picture summarizes that all the interconnect. We can see the NVLink 5.0. It has 3.6 terabyte per second for the external module level interconnect. And then it has the die-to-die interconnect here. It's connected to GPU die here. It's 10 terabyte per second. And from two GPU the GPU also has another NVLink. It's called NVLink C2C. It has 900 gigabyte per second bandwidth here. Yeah. So that's the high-speed interconnect technology used in the GPU, the most powerful computing chip I think in the world. And for another high-speed interconnect, we often talk about this the memory bandwidth, memory interface, and the memory interface also increased a lot, starting from less than 1 gigabit per second per pin. Right now it's almost close. I think the new spec we're considering more than 62 gigabit per second per pin. So that density is really large, and the per pin speed is also really large. So in that situation, to improve the bandwidth efficiency in a very small form factor, so a lot of single-ended signaling is used, and at this situation, the crosstalk is the worst. It's very worse and worse. This crosstalk situation. So here's two standard channel we see in the high density interconnect. One is for a DDR memory. Is this on-chip. When crosstalk is on the PCB or the server board, and this is HBM's interface. It includes the 3D interface and also the 2.5D interface on the interposer. So the crosstalk specs for these two channels also the tight crosstalk is also very tight and more and more even more and more harder. Yeah. So I just talk about the situation we meet in the modern AI related computing system. So my research I focus on how to solve this crosstalk in an efficient way on this situation. So I have two case studies. One is using the crosstalk cancellation coding schemes. We created some different compared a lot of different coding schemes to avoid this crosstalk and as more as possible. And the basic we use is, let's say we add some redundancy on the channel. And we found the worst situation when the crosstalk happens. So using that coding scheme, we're trying to remove that code. So we have some redundancy in the channel, but at that cost, we reduce the crosstalk between adjacent channels. So that the basic, we start very simple considerations. And even for these simple considerations, the experiment result is pretty good. We fabricate a 28 nanometer CMOS chip to demonstrate our Fibonacci coding. That's one of effective coding we found. Is the first line is the we're trying to use the bad channel. So the channel condition is really bad. We design it in a very bad condition, and we without coding crosstalk cancellation coding we're trying to push the maximum bandwidth, and then we can observe the I is almost close at 6 gigahertz over 8 inch PCBs there. And then at the second line, we opened our Fibonacci coding, which used to cancel that the crosstalk. And we can see the I opens a lot, and BR, so bit error rate is also reduced. So there's more detailed testing result to show our jitter improvements and also the BR improvement. And the good thing is the power overhead and also the area overhead hardware on the chip is really small. So we achieved the state-of-the-art performance on this crosstalk cancellation technology. This is more details on this GSS's paper. And another study, similar situation, we adopt this crosstalk cancellation scheme in the RF interconnect. So RF interconnect is we're trying to use RF technology, which is dominant in the wireless communication, and we use that technology on the connected or not connected, but it's really close when the transceiver, the TX and RX, really close in that situation. And here's the baseband, and this is the modulator, and then we sum it together. So the structure is really exactly the same with the wireless transceivers. And here's the first demonstration is we're trying to remove the copper contact in the, let's say, USB and HDMI connector. We remove that copper connection, because when copper connection, when we use it multiple time, the speed is higher and higher. The channel condition is really sensitive to the surface of the metal. So if we can remove that metal, connect by some contact is without copper contact. So it's basically wireless, or it's connected by some waveguide. It's just not the contact of the copper. In that situation, we build a 60 gigahertz transceiver, which can use different modulation. Also, we use some pre-distortion technology to improve the eye diagrams condition quality. The energy efficiency achieved is also 28 nanometer, is 6 picojoule per bit. Yeah. Another demonstration we found for this contactless RF interconnect, we found a pretty interesting application is on the top level is a CMOS imaging sensor chip. And then at the bottom is a logic die, which supposed to use to do the signal, image signal processing. In that condition, the lights usually come from the backside of the CMOS imaging sensor chip. And previously, for this 3D integration, it needs the TSV, which is expensive, and also there's some yield issue for the TSVs through silicon via technology. For this interconnect, we use an RF interconnect to remove that TSV vertical vias for these two chips. And these two chips, we can just put them together and put some glue on it. The interconnect between the CMOS image chip to the logic image processing chip are connected with each other. And we make because the CMOS image sensor, the circuits on that part is optimized for the display or the sensor of the light. So all the logical and the device the performance is pretty poor. So we put all the transistor needs high performance on the bottom of the digital chip. So they come to be different technology nodes. So we made this and demonstrate this using a 20 gigahertz as a carrier frequency and achieve a 200 megabyte per second data rate. But that's limited by I think the speed is not limited by the channel or the integration itself. It's limited by our modulator design. So actually this interconnect bandwidth can achieve more than 10 gigabit per second per channel. We have some design issue in this chip. It's not perfect design. Yeah, come back to the crosstalk cancellation scheme. If we can use the RF, the multi-band communication in this crosstalk problem-solving situation, we have another new domain in the frequency domain to avoid that crosstalk. That's what we do in the wireless communication. We have other person using Bluetooth, right? We can easily use different frequency to support different users. Yeah, we can see if we have two bands, one is baseband, and another is the RF band. These two band frequency can separate with each other. We can on the communication domain we can separate the time and separate the frequency band. Then that's another isolation between the two adjacent channels. That's basically what we're using. And also here's the demo. This eye diagram is the eye diagram without any crosstalk. So just one channel is active. And this one is if we active all the channels adjacent together, and then the main channels BER eye diagram quality is decreased a lot. And then when we use our dual band signaling to add a frequency domain as isolation technology, then our eye diagram is completely opened again. That's we're using the frequency isolation to provide another domain for the crosstalk cancellation. Yeah, that's most of my. So in summary, for the interconnect between chip to chip, we're trying to make the data transfer efficiency within unit area at the unit time. We need to send more and more data. So there's a lot of directions to go denser, go faster, and go higher. That's all directions make the crosstalk worse and harder to make the crosstalk cancellation. So I think this is the important problem we need handling for future, especially for advanced packaging technology import together. Yeah. So I'm also working on some more flexible interconnect between chips, like the RF interconnects, also the some silicon photonics interconnect. Also add some special designed coupler or waveguide to extend the distance between two chips. Yeah, that's all. Thank you. Here's my yeah. Thank you. Here's my group. Thank you. So welcome to Nanjing University in China. It's a very beautiful campus. Yeah. Thank you.
Any questions? Just one question. I'm curious about the RF communication in this frequency
bands you consider
You're talking about this one.
yes, in which RF band you consider, because I remember some years ago, Subterahertz chip-to-chip communication was captured a lot of attention.
Yeah, actually, we built I started this period very long period of time. So we tried a lot of frequencies, and for this study, we use one baseband DC and one 60 gigahertz carrier, and then in another demo here for this one, I only use one band. That's I think it's around. I think that's around 120 gigahertz, something like that. So our group working on starting from the 5 gigahertz to even more than similar to your research. We're working on the D band, which is around 150 gigahertz, something like that. So this is full band. So the RF interconnect is a concept. The frequency you can choose based on the application you want to choose. Yes.
Okay, so thank you again.